Today's topic is the columns, and normally we have two types of columns. We have long columns like this one. We have short columns also. So to demonstrate that, we have this is the short column here. If you see the way that the short column fails and crashing, it just crashes, whereas the long columns like the one on the right, it fails in buckling. And these are two important factors that we take into account. Of course, in this we will just cover the long columns or cylinder columns. The main factor and one of the factors, not the main factor, is the height of the column, like this one. So this is important. And the second thing is the way that this column is supported. So this is one of support and this is other support. Now in this example, the support is type fixed and this is hinge. So this will affect the way that this column buckles. To demonstrate the pattern of buckling, we have these three categories, which will be the main ones that we'll cover in this course. There's more than these categories, but we'll cover only these three. So you see in the case of hinge, this one, the column will buckle in this way. So meaning it will buckle through the entire height. So from here to here. Now if we would like to do some sort of comparison between the hinge and the hinge fix and fix, we'll have some sort of a factor called K. So in this case the entire column buckles. So the value of K is equal to 1.0. So meaning the entire thing will buckle. So if the entire length is equal to 20 feet, then KL is equal to 1 multiplied by 20, so the length that is buckling is 20 feet. Now if we go to the hinge fix, this will buckle. The hinge part doesn't resist any moment, so it will buckle freely, but the fixed part will resist buckling, so it will be some restraint like that. So meaning that the length that will be buckling is only this part. So the K value, or how much of the entire length is buckling, is 0.8. So if you have, for example, 20 here also, then the KL, the effective buckling length, is equal to 0.8 multiplied by 20 feet and is equal to a certain value. So 0.8 multiplied by 20 is equal to, so will be equal to 16. So that will be the length that we should be dealing with for buckling. Now if we come to fix, in that case if you look at the way this is buckled, is only buckling on this area. So there's a resistance at this and resistance at this. This is fixed and this is fixed. So the amount that is buckling is only this much. And this is, the K is 0.65. So now 0.65 multiplied by 20 feet, assuming the length is the same, then in that case the effective buckling length is equal to 13 feet only. So of course this is strongest, this is the weakest. So these rules will be used in the design of column. Now let's go forward to the main equation of buckling. So as we know, if you look at the stress here equation, so it says this is the stress, this is the force, and this is the cross-sectional area. This is what we learn in strength of materials. Now the question will be always in the design of column excuse me, is that we will be given certain measurement for the section. Say this is W12 by 58, and the question is how much axial load this column can take. How much is this axial load capacity? How much PA is equal to? As you know, this is maximum axial load, this is maximum axial stress, excuse me, and this cross-sectional area. So once you are given a section, you should be able to know what is the cross-sectional area of it, because that is from the properties of the section. Now all you need to do is you need to find out what is the value of axial stress. Now axial stress is related to the cylinderness, to the KL over R. KL, we already know what KL is the effective buckling length. R is the radius of gyration. The radius of gyration is derived from the moment of inertia. This is why we see X here, because this could be Ry, and this is equal to moment of inertia about X divided by cross-sectional area. So it is proportionally relevant to the moment of inertia, and moment of inertia is the strength of the section. So we need to find out the KL over R to be able to find the value of A. Now Rx and Ry are properties like moment of inertia, Ix and Iy. You find them in the properties of the section. So again, once you are given the property, you are given the section like the following, W1258, you should be able to know what the cross-sectional area is, what is the Ry is, and what is Rx and Ry are. So again, if you go to the procedure, it is a straightforward procedure. All you need to do is, given the section, when you are given the section, you will know what is the cross-sectional area, and you will know what the value of Rx and Ry is. All you need to do is you need to figure out this FA, and FA can be figured out in a table. So we have tables like so. Once you know the value of KL over R, you should be able to get the value of FA. So once you get the value of FA, so this table will be based on two types of steel. We are doing steel design, of course, for columns. There's C36 and there's C50. These are the two grades of column. So so once we get the value of FA, then after that will be straightforward, because the equation now becomes PA is equal to FA multiplied by cross-sectional area, because now I got the value of FA from the KL over R, and the cross-sectional area is already given. So let's go through an example to explain the entire concept here. So we'll do an example. Say we have an example. In this example, it's given that the section is W12 by 53, and it says the steel type is FY36, means that we'll use C36 table for it. And the question is, calculate the value of PA. What is the maximum allowable axial load? What is the maximum allowable axial load, which is this PA. So there are three steps, straightforward steps. The first step is we would like to get the value of KL over Rx and KL over Ry. What does this mean? We need to see what is the buckling about YY, which is this. What is the buckling about XX? That will be in the front direction. So let's break this down. So step one is to calculate the KL over R, X and Y. And second step, once you get the value of KL over R, you should be able to get the value of FA from the table. 3 is you just apply this equation, PA is equal to FA multiplied by the cross-sectional area. These are three straightforward steps. So in this case, we have to do a study of KL over R, because we need to get the value of KL over R, X, and KL over Ry. So I'll do that. So we have the buckling about YY. So step one is the study buckling. So step one, if you want to, step number one, buckling study. So in the buckling study, we are doing the buckling about X and buckling about Y. And we have to agree about this to be in sync. Now you see this is about Y. This is Y. So it will buckle in this direction or this direction, doesn't matter to us. So the buckling is again about Y. This is Y. And there are no lateral support. So let's see, and this is given as hinge and this is hinge. So for a case of hinge, if you go to these cases, see hinge will give us a K value equal to 1. Okay, so I'll use that. So the K value, as you can see here, it is equal to 1, and the entire length is given 16. So, and Ry, if you go to the tables, you'll see the value of Ry for this type. Let's get that value. Now we have a section W12 by 53. So if you go to W12 by 53, so here is so you see W12 by 53, it has the Rx is this and Ry is this. So you have 5.23 for Rx and 2.48 for Ry. You have the area 15.6. So this is not going to be given, but you have to get this from so it says here you have the R is equal to 2.48, and of course Rx is 5.23, and the area, we'll come to the area later. So what we do here is we apply this equation, KL over Ry, and K is 1 and L is 16, and you need to multiply by 12 because the Ry is given in inches. So if you leave this as feet, then the answer will be wrong. The entire answer will be wrong. So just be careful, because this is not, you will not get the right answer, so you'll get the entire thing wrong. So you need to pay attention to the units. You must multiply by 12. Anyway, so we get the value KL over R equals 77.4. We always round this up. And do same thing for buckling about XX. Again, this is XX. Again, this, if you look at this and you compare, this is the X. So the buckling about X again is like that. This is hinge and this is hinge, and the K value is equal to 1, like in this case. The only thing is different is the Rx is different. So we get a value of 36.7, and you round this up to 37. Now in step number 2 is we select the largest value of these KL over R's. We select the largest value of KL over R, which is 78 in this case. And if you go back to the table again and see as the KL over R gets larger, the value of the axial stress is less. So if you look at 1, for example 1, this is 21. Now if you go to a value of 130, for example, see the value of FA is 8.84. FA is the maximum allowable axial stress, meaning the stress, how much stress can take. So the larger the value of KL over R, the less is the resistance of the column. So in the design, as you know, the concept is always we take the weakest part, so meaning that we know in this case it will fail in the weakest part before the strongest part. So step number 2 is that we says choose the largest value of KL over R. In this case it is 78, and go to FA, see what is the value of that. So if you go to a value of 78, we have, first of all, this is we have this is 36, so you have to use C36, and the value is 78, so look for 78 here. This is 78. So you see the value of FA, this goes to FA. This is FA. FA. So the value for 78 is equal to 15.58. So now, so as you see here, it says table C36, which was the table that we've chosen, and the FA value is 15.58. Now step number 3 is just a matter of multiplication. So we go step number 3 is calculate the maximum. Says calculate the maximum level, and you apply this equation, which was the main equation of the, we have the cross section at 15.6 from table, so all we need to do is apply this equation, 15.58. again, put the units, it is kip per inch square multiplied by 15.6 inch square, so you get value in kips 240